Hello, my name is Joel Siebold, and today we're going to talk about recursive time series segmentation algorithm in a high-performance big data computing environment. So my agenda here is to discuss some of the challenges in implementing what is really quite a sophisticated time series segmentation, or sometimes called change point algorithm, in a big data environment using financial data. So there's going to be a new paradigm that will enable this to work, and it's a new kind of workflow, and we're going to talk a little bit about some details on what that workflow is. I also want to discuss what segmentation is and why it's useful for time series, then how one would go about implementing such a recursive algorithm in a big tick data environment, discuss some results, and also discuss some further areas for work, and then we'll open things up to question and answers. And also interspersed along the way, we'll have some code samples. We'll show you how we implemented the code and how we ran the code in a couple of different ways. And these code samples will be made available to you after the webinar. So now I want to get right into what we're doing and discuss a little bit why it's important and interesting. So what we're really after is to divide a time series, in this case, a time series of trade data or tick data, into its natural segmentations. And what I mean by natural segmentations means where the net buying and the net selling or net balance is occurring along the time series. And the general picture is laid out by this sequence going from left to right, where we have a time series signal defined by the signed volume. So every trade in the time series is associated with a volume and also a sign, a plus or minus, depending on whether the trade is associated with an uptick, in which case we say the trade was initiated by a buyer, or a downtick, in which case we say that the trade was initiated by a seller. And the aggregate of these signed volumes will determine where the patches are, where the net buy patches are, and the net sell patches are along the time series. So what we're showing really is the basic input variables here. So we have a sliding pointer, which must reference every trade in the time series and potentially divide the time series into patches. In this case, we see an example of potentially a buy or a sell patch on the left of the pointer, and a very noisy patch on the right, which doesn't appear to have any net buying or selling. And we want to maximize the differences between these two segments, and that will tell us where the patches are in supply and demand. So just to give you just kind of an idea of these variables, so the mean of the buying selling in aggregate to the left, we calling mu sub left, and to the right of the pointer, mu sub right. And we want to maximize. We form from this data for every record or every position of the sliding pointer, we calculate a t-statistic. And this statistic is simply the absolute value of the difference in the means of the signed volume, the total signed volume, to the left of the sliding pointer and to the right of the sliding pointer. And then we come up with a question which determines where the cut should be made, namely, is this t-stat large enough compared to a random reshuffling of this time series such that there's a less 1 out of 100 chance that the largest difference or the largest t-stat here came from a randomized sample. We want to locate those the maximum values of the t-stat, and determine whether or not that t-stat is significant compared to a random reshuffling. That's the basic idea. So we can identify these patches, these natural bicell regions or noise regions in the time series. Now, the question is, so why doing this? Why is it interesting case? So in general, time series are obviously very important type of data. It's very general kind of data that applies to not only finance, but also medicine, biology, geology, business intelligence, manufacturing, and so on. And it's interesting to try to implement an algorithm like this in a big data environment, particularly because the relationship between the records is not known beforehand. So we're not doing binning by a fixed interval, say minute bins. We're not aggregating in fixed bins. We're going to let the algorithm, through a segmentation process, decide for us where the natural regions are of this time series. And this is something that I believe would be very difficult to do in traditional SQL due to this recursive process, and also the need for both having the entire data set available to you and also having a sliding pointer, being able to implement a sliding pointer, which in traditional SQL I think would be very difficult. What this allows us to do in general would imagine compressing a large data set into these patches. So it gives a tremendous amount of compression, which could then be used further in clustering different time series by behaviors or determining what the properties of the different patches are. For example, perhaps a net buy sell patch may have different volatilities or liquidity compared to these noise patches, and that might impact the way you trade or the way you monitor risk, measure risk. Also, the data is more stationary within patches than across patches. So a lot of techniques to work with data become more convenient and easy to interpret within each of these identified patches. Also, the fact that we're doing a binary segmentation here, it's going to be more, say, better performant than more of a brute force kind of way, which typically segmentation algorithms quadratic or worse in complexity. And this algorithm, while not guaranteeing a global minimum, for example, it would be a type of n log n complexity. So we should get good performance out of it. So now I'm going to talk a little bit about some of the challenges in dealing with tick data, which most of you, I'm sure, are aware is typically a headache. So the old-fashioned way of thinking about tick data is you would have to make some request for a large volume of data, then you would wait for it, figure out a place to store that data. Typically, it would be a cluster of servers, maybe an Oracle database, or maybe a Hadoop-based framework. And then having the data in that kind of environment gives you access to very powerful SQL-like or Hive SQL MapReduce-like functionality, which is great for scalability and kind of batch processing. But for time series, I found that the analytics in working with fine-grained data and time series is kind of clunky at best. There are other tools like R, Python, MATLAB, and so on that offer very sophisticated time series analytics, machine learning, modeling, visualization, and so on. But implied with the use of these tools is the need to have the data stored locally in order for you to be able to work with it. And what we're talking about here is a different kind of a paradigm where our sophisticated analytics is happening where the data is sitting without having to move such large data set. Now, I would have to also talk a little bit about the architecture and the technology that's enabling us to do this kind of work. So as you can see here, this high-level picture shows on the left various data sets and content that Thomson Reuters is known for. In particular, what we're looking at in this case is tick history data. We also have ability to work with real-time data, third-party content, and other different kinds of data sets. But velocity analytics hides most, if not all, of the complexity of these different collections in what I would call a coherent form of storage, an accessible form of storage, both on disk and in memory, enabling a user coming on the left-hand side here through either API or through the IDE provided to you to interact with the data in such a way so that the complexities of different collections is abstracted away from you. And you just get to play with the data using many of the out-of-the-box analytics functions that come with this technology. Also gives you the ability to create your own user-defined functions, third-party analytics libraries, and gives you a chance to store and persist all of your objects and functions in this framework. And all you have to do is write your code, execute the code on the server, and then when you're ready, after doing whatever aggregation or analytics on the tick data, to move that data into your client, whether it be R, in which case I'm most comfortable with, so we'll be focusing on R, but you can also work with Java, Python, and so on, all popular languages, and then do the more sophisticated stuff at high end, like machine learning, predictive analytics, and visualizations. Do it in the client where it's really best optimized, and all the heavy lifting is done for you within the VA8 platform. Okay, one thing I want to mention, you can see Q here as the native language for velocity analytics. That's, for those of you familiar with Q is very much associated with KX database. So the database component for velocity analytics is a KDB database. So I just wanted to make that point. And now what we can do is a little bit of a demo as to how we would run the basic tick extraction from R. And for that, I built a simple wrapper which allows you to format a list of input to set up your query. In this case, the query is for a day's worth of Apple trades, starting from 9:30 to 4 p.m. And get_ticks is a simple R function that I wrote, which converts this structure into a Q-based command that velocity analytics can understand and execute. An important point that I want to make before I do that is explain to you that the input variable here to the getTicks function is the variable name that gets stored on the server. It tells velocity analytics that the data that we're requesting has to stay on the server and not, at this stage, to be uploaded or in this case downloaded to the client. We don't want to be downloading large amounts of tick data at this stage. So what I'm going to do now is bring up this code again. And this is my simple notepad file, R file, and just going to grab the getTicks data here, the list of inputs. Now you can see this, it really speaks for itself what these parameters are, so I won't really go much into detail other than, again, to reiterate the importance of the store as variable to keep the data at this stage on the server. So we're going to copy and paste that command so we can see what it looks like. And actually I've done it already, but there's no harm in copying it again. So what is the actual velocity analytics command? What does it look like? So this is the formatted Q command that says get ticks for this brick or stock apple.oq and format it in a way that Velocity Analytics understands. And if for those familiar with Q variable declaration, TST_TAQ is the variable that we're storing the tick data in that's going to live on the server. And if we want to execute that command, since I have it already in my R shell, I'm going to just simply execute that command, and the tick data is retrieved pretty quick, I would say. And it's living on the server, and in order to see that data without having to download it, I just go to my IDE to interact directly with the variable storing the data, in which case we called it TST_TAQ. And in order to just see that data, we're just going to execute, give me the first 500 lines, 500 records, and there's the raw data. So we have different timestamps, exchange system timestamps, we have our symbol, price, and volume, and much more than that, which we won't go into any detail on right now. But really the important point is the data is now living on the server, and you can execute your next commands from the client, and will interact and process the data on the server. So just to remind you, what we're doing here again is we're segmenting our time series of signed volume for Apple, in our case, looking to detect imbalances in buying and selling versus sort of noise regions. And so our algorithm relies on having all the data in the time series available in order to do this top-down recursion, and also the ability to have data sort of slide past a pointer, right? As we move the pointer, the data slide is streaming past the pointer. So I just want to make a comment that what we're making really use of here is, in the signed volume, is this flag called the Lee-Ready tick flag, or the Lee-Ready tick rule, which says that each trade can be assigned a plus or minus sign depending on whether the closest tick, most recent tick to the current trade where the sliding pointer is, was an uptick, in which case there would be a buy, or a -1, in which case the most recent tick was a down tick, and that would be a sell. And the signed volume, just to remind you again, is the multiplication of the flag times the number of shares. And I also want to, at this stage, reference two great papers that where I first discovered this algorithm was in the paper by Stanley et al. And that paper was applying the algorithm to physiological signals, for example, heart signals and EKG signals, to detect healthy transitions and distinctions between healthy heart time series and a diseased heart. And the second paper that uses this algorithm is coming from an application more closely related to what we're doing here, looking at size scaling laws of large agents in the market. So now I'm going to move on to implementation of the algorithm from the point of view of the flow of the program. And we've already shown that we've demonstrated that we could get the ticks, and the data will remain on the server until we decide we want to download it. But we keep the data on the server and create data structures that we need in order to get the algorithm to recurse through the time series and discover these buying and sell patch. And the data structure that we need to do this is something I just simply call the patch table, which represents the extensive compression of the time series, where we're representing each patch by a simple ID, iteration ID, a start index, an end index, and most importantly, a flag that tells the process whether or not a given patch has been tested, in which case we set the flag to -1, to 0 if the patch is a leaf segment, cannot be cut further, or is set to 1, in which case a given patch can be cut into 2 left and right segments. And the recursion essentially is a while loop that pulls any patches which need to be tested from the patch table. And remember, we do initiate the patch table. So initially, there will be a patch to test, at least coming from the topmost level or layer. And if there are patches to test where we have our isCut parameter or flag set to -1, then we need to decide whether the patch that is to be tested, if there is a significant cutting point for that patch. And of course, if there are no patches to test, that's the signal for the loop to end. Now, there are two choices. When there is a cut to be made, if the t-stat is deemed significant, then on the left we see we have to do an update, which means yes, the current patch is cut, and then we insert 2 new patches, a left and a right patch, each with an isCut flag to -1, meaning keep testing. If there's no significant cut to be made, then all we have to do is update the parent patch to set the isCut flag to 0, and the parent patch now becomes a leaf or end terminal segment. Now I want to talk a little bit about the application structure to support this program here. And this is really a division of labor, which was convenient to work with, since VA8 and KX are Q native. Q is and QSQL is native to our analytic framework. I created a set of functions to help, since I'm working in the client, I'm more familiar with R than I am with Q, and I like working with R. So I created a bunch of generic utilities to help me convert commands from R strings to Q that will hide a little bit of the idiosyncrasies in Q that we're maybe not familiar with. There's also the ability to create utilities as user-defined functions, which we can ship to this Velocity Analytics server and have them persist there and be able to call on them when we need them. And then, of course, there's the main workflow. So these 3 sections I found convenient. And what we gained from this kind of architecture is really incredible benefits of having Q and QSQL at the same time maintain the time ordering, which is critical for the sliding pointer kind of processing. Also, we take advantage of features, Q type and KX and VA8 features, which allow us to persist all of our functions, our segmenting functions, on the servers and use them when we need them. The performance at the level of the server is really, what we're really doing is exploiting the Q language and the fact that it's in columnar-based, in-memory database, making it very fast and perfectly suited to do time series analytics. Okay, so what I'm going to do for you now is execute a little bit more code and give you a little bit more transparency into some of these functions that are critical to the cutting process, the segmenting process. And the key function there is something I call getCurrentCut. And what it expects as an input is simply the iteration index. the starting index and the right index, which is end index of the current patch. And it will extract tick data for the patch and then constructs all the inputs and does all the calculations necessary to get the T statistic for every record in the patch. So this really implements our sliding pointer, ultimately finding the pointer position where the T-stat is a max, where the proposed cut will be, and then returns the two proposed child patches. So I need to show you first a couple of very simple helper functions, and I think you just get a sense of how really simple the whole thing is using a QSQL query, but making use or exploiting vector functions such as getLeft and a sequence function, which both of them simply return vectors given an input or set of inputs. The getLeft function will just return a vector whose indices are up to the input parameter, and a sequence does exactly what you imagine. You pass in a start integer, an end integer, and an interval, and it will return a vector representing that guy. And so these are used in this very simple select statement, which I would say, I could be wrong about this, but would be very difficult to build a command like this in traditional SQL. So what I'm going to do is go to my Delta IDE, show you what these simple functions are, and run this select statement, and then you see the expression of the sliding pointer calculating the left signed volumes and the right signed volumes for every record in the patch. And so you get a sense of how that works. So here's my IDE. It's already lined up, and the function getCurrentCut, which we said accepts start, end, and iteration index. And we're going to run, we have just some temporary results here that we're going to rely on, which I've conveniently already run. And I'm simply just going to execute in my Delta IDE the command returning the sliding pointer result. And it's executing now. Okay, so this is a result which, again, as I mentioned, I thought would be very difficult to do in almost any other environment that I've personally worked with. You kind of see the sliding pointer here. So every record splits out the left and the right volumes, the signed volumes, relative to the current record. And so these then go further on. In this function, we'll calculate means, for example, of the left volume, the mean of the right volume, and ultimately resulting in our T-stat calculation for each record in the patch. So that's really, I felt like this was, in a way, the main result in some sense, because it's showing how this technology and how this database and language and VA8 all work together to produce results very simple, one SQL line of code where all the data is split using a pointer, a sliding pointer kind of processing that would be extremely difficult using traditional SQL or MapReduce methods. So now what I'd like to do is show you some results for Apple on 3/16, one day that we picked to run the segmentation. And what the end result looks like is a set of patches with start patch ID, end patch index. And also you can see that all these patches are leaf patches. And we also tagged on the signed volume fraction, which gives us the strength or the level of the imbalance within each patch. And you can see we have sort of short bursts of buying, two buying patches, and looks like a couple of selling patches here, separated by noise, what looks to be very low level imbalances and noise. So this is the end result of the process. What I could do is look a little bit closer into some of these patches and plot the market impact profile for each one of these patches of at least 100 trades or more. And you can see that we have, so market impact, I should actually say what that is. It's the logarithmic return of the price for every trade executed relative to the opening price of the patch. So you can see we're starting at 0, and for the sell patches, the market begins to move against. If it's your trade that, or a series of trades that are selling at such a high rate compared to what the volume is doing, the market will move against you. The price will go lower if you're trying to sell. And similarly, you can see here a buy patch where if it's your order that's responsible for 99% of the market volume, which admittedly is very high, but at least one can imagine a case where that might occur. The market, as your order is executing, the market moves against you and raises the price. And this convex shape, you can sort of see the convex shape here a little bit, is really a classical shape of this type of curve called the market impact curve. Now what I did to the right here is I took this very strong buy patch of about 100 trades and extended into the next patch, which looks like a noise patch. And this is in the literature where people say that to the left of the red line is the actual the buy patch, and to the right is the noise patch. You can see that what people call the temporary market impact is how the market responds to an imbalance while the imbalance is being executed. And then after the imbalance completes, the price, if you like, re-equilibrates. You can imagine a sort of average level of this noise. The market decides, well, we think the apple should really be somewhere here. And people call this the permanent impact of the imbalance. And what I've encouraged by is a most beautiful plot from paper by Mantegna, Farmer, et al. On market impact trading profile for large trading orders in stock markets. It's really one of the nicest plots that I've seen in all financial literature. What they've done is looked at a very large scale, and they've taken many of these patches for 2 exchanges, done some rescaling, which is not too important. What is important is that the scaling collapses all of these many patches onto single curve. And for different exchanges, the shape of the curve may be different. So you're seeing microstructure effects here. And like I say, they're averaging over many of these patches and many stocks. But the fact that we're able to, in our own little way, simple way, reproduce some of these features using SQL and a big data environment is extremely exciting. And so I'm going to end it here and open things up to questions. But first, let me just summarize. What we did was we showed that we could do very interesting compression of data time series using a segmentation algorithm, which provides some context for market impact, could be used for further processing like machine learning, classification, clustering, and so on. And we could conclude that velocity analytics was a very useful architecture to be able to implement such an algorithm at the tick level where the data sits and at scale. Some further work along these lines, we could look at statistical properties of these patches. How would a buy and sell patches differ from noise patches in terms of volatility, liquidity? Of course, we want to look at more data and also scale out to many more stocks. And now we can open things up to questions. Thank you very much.